Hi guys, in this episode we continue expenditure functions. So first let's talk about the graphical intuition behind the expenditure functions. All right, so here is, if you remember the formal description, is we would like to minimize the expenditure, which is in the too good case. Expenditure would be price of good x times x plus price of good y times y. By choosing x and y in non-negative real numbers, subject to the constraint u of xy is greater than or equal to u bars, right? That was the problem. So what does that mean? That means graphically, I'm trying to do the following. So I have x here, I have y here, and this is the indifference curve where the utility level is equal to u bar. I am happy if the utility achieved by consuming x and y is greater than u bar, meaning we are on a higher indifference curve, but this should be the limit. I don't want to go any indifference curve below this. Perfect. Well, so this is kind of my fixed constraint. What about my objective? Well, my objective is basically the expenditure function. So what is an expenditure function? Well, remember, this is more like a budget constraint. So I would like to minimize this pxx plus pyy term. All right, but I mean, this is not equal to something, right? How can I drove this? Well, simple, just set this equal to some constant k and drove it. So this is, let's say, the x-intercept is therefore k divided by px, and the y-intercept is k divided by py, as simple as this. So therefore, this is my sort of expenditure line, all right? But the thing is, don't forget, the objective function is the expenditure. So this k is not a fixed number. You can vary it because I am choosing the expenditure level, fixing the utility or the indifference curve. So that means there are infinitely many varying expenditure curves that I have. So as we move in this direction, that means higher expenditure. Higher expenditure. So if we move in this direction to the 0 point, that means lower expenditure, obviously, because you consume nothing. So if x and y are 0, well, your expenditure will be 0. So the thing is, I would like to minimize the expenditure, satisfying this constraint. So obviously, consuming 0x and 0y, right, is going to minimize my expenditure. It's obvious, but the problem is my utility will also probably be 0. It's definitely going to be below this indifference curve. So therefore, 0, 0 is not optimal solution for this problem. Well, is any point on this line optimal solution? No, none of them. Why is that? Well, because yes, the expenditure is minimal corresponding, in comparison to the other lines. By the way, just to make sure that any blue line indicates the points x and y's where the expenditure is equal to k, all right? Once again, any point on these blue lines indicate x and y's where the expenditure is equal to k. Any point on this black indifference curve tells us the x and y's where the utility is equal to u bar, all right? Okay, so any point on this blue curve have lower expenditure than the others, but the thing is none of them are going to give me the u bar utility because they are all lower than the indifference curve. And remember, the indifference curves move in this direction as we go in the northeast direction, higher utility, sort of southwest direction, lower utility. Okay, so therefore the optimal solution is basically, at least graphically here, where this point is going to give me the utility level u bar, and it's going to be minimizing the expenditure. I mean, consider this point. This point is giving me u bar utility, which is exactly what I want, right? But its expenditure is higher because this expenditure curve is lying beneath it. So this is less costly than this, all right? Meaning to drove this, I need to pick a smaller k than to drove this. So that means the expenditure here is less than the expenditure there. Or, I don't know, pick a point here. Same expenditure with this one, right? And definitely higher indifference curve, because an indifference curve passing from this point is going to look something like this. So I give higher utility, right? But look, what I want to do, I want to minimize the expenditure. And the thing is, I want to be higher than U bar. So yes, this is strictly higher than U bar, and the expenditure is way too much. I want to minimize the expenditure. So my first concern is to minimize it. But the thing is, I don't want to go below U bar. Okay? So therefore, the optimal solution must be this point. So this is the graphical explanation. Well, by the way, what does this point mean? It's like the slope of the indifference curve, which is marginal rate of substitution, equals to price of the, not budget curve, but the ISO cost curve. All right, so these blue lines, by the way, we call them, well, ISO cost, ISO expenditure curves, all right? So therefore, its slope, which is minus px divided by py. So exactly the same thing, right? I mean, if you remember the utility maximization problem, margin rate of substitution equals price ratio. Same thing here, the margin rate of substitution is equal to the price ratio. Okay, so one question. We already talked about how we derive mathematically the Lagrangian. It's simple. It's the pxx plus pyy, the objective function minus lambda times your constraint, which is u of xy minus u bar. Right? This is the Lagrangian, so you solve for the first order conditions. The question is, though, when I find, so I'm going to clean this. So this is the expenditure minimization. Let's remember utility maximization. Utility maximization problem. We already know it. I just want to remember, at least graphically. So graphically, the idea was I have one budget line. All right. So its slope is minus px over py. And then I have many indifference curves. And so the optimal point is this, where MRS equals minus price ratio px over py, right? The Lagrangian problem for this is u of xy minus lambda times xpx plus ypy minus income. I don't write down the Lagrangian for n variable because, you know, our arguments are not going to be different if we have two variables versus n variables. The Lagrangian in the expenditure minimization problem, however, is pxx plus pyy minus lambda u of xy minus u bar. Okay, so once we solve this, we're going to get some x star, the optimal x star, and y star. And here we're going to get some x star, but let's call it x double star, y double star. Question is, meaning x star, y star solves this Lagrangian problem in order to maximize this utility function, and assuming that the utility functions are the same in both environments, and the prices are the same as well. And this x star, y star solves this minimization problem. So the question is, this is why I put x star here and double star here. Are they the same or different? X star, x double star, y double star. Are they the same or different? Well, the answer is, in general, they do not have to be same. And in fact, I think that's pretty obvious. One reason, yes, graphically, they look very much the same. I mean, marginal rate of substitution, price ratio here, marginal rate of substitution equals price ratio here, right? MRS equals minus px py, we just said. Yes, but be careful. This is just one of the conditions for optimality. The second condition here is the constraint. U of xy must be equal to u bar. So I will have one equation coming from this, the second equation coming from this constraint. So two equations, two unknowns, I'm going to solve x star, y star. Here, however, my constraint is xpx plus ypy equals income. So I'm going to have two unknowns, two equations, and solve x double star, y double star. So that means in these two different problems, I am solving different systems of equations. And hence, understandably, those optimal points do not have to be the same. And in fact, they can't be the same because here there's a parameter EI, income, and here there's a parameter U bar that I am using. And so here the x star should be a function of Px, Py, and U bar. Same for y star, Px, Py, U bar. However, here, my optimal x double star should be function of Px, Py, and income. Same here, y double star must be a function of Px, Py, and income. So obviously, they shouldn't be the same. They may be, but that's an exception rather than a rule. All right? So that's very important observation. In fact, later in a few videos afterwards, we're going to call these guys as Hicksian demand. All right? And we're going to call, the other way around. I'm sorry. This is the utility maximization. So we're going to call these demands Marshallian demand. And we're going to call these as Hicksian demand. Why we give different names? Well, obviously because they're different and the idea of their intuition are different. We will later talk much more in detail about why this is Marshallian demand, Hicksian demand, or what's the difference between these two, or what's the relationship between these two. But they're coming much later. All right, not now. All right, very good. Well, now I want to say a few things about the relationship between expenditure function and the indirect utility function, all right? Without talking about the demand. So here is what we can say in general. Whenever, assuming that your utility function is continuous everywhere and it's increasing everywhere, all right? Then the prices are obviously positive. There's no zero price. Then the indirect utility function and the expenditure functions are in fact related concepts. They're not too different from one another. How so? The expenditure function, which is a function of price, all right, so P is a vector, like P1, P2, or Px, Py, up to Pn if they're n goods. So P is a vector of price. All right, so let me just say so. Vector of price. So expenditure function is a function of vector and of price and the U bar, if you remember. And then the indirect utility function is again a vector of price, a function of vector of price, and then the income, right? So here the U bar and the indirect utility function are somewhat related, and in fact they are. So if I write my expenditure function as a function of price vector, and then instead of U bar, I just plug the indirect utility under this price scheme and this income scheme, and then calculate my expenditure, well, this should be equal to the income I. All right, let's come again. The minimum expenditure, the minimum amount of money to attain this indirect utility level, indirect utility level sounds stupid. Come again. So the minimum expenditure or the minimum amount of money I need to attain this level of utility under price regime P is equal to income of this consumer. All right? And symmetrically, if I have an indirect utility function, the maximum level of utility I can get under the price scheme P, when the income of this individual is his minimal expenditure to get this utility level U bar, actually this utility level must be U bar. Okay? So let's show them. So this is how the expenditure function and indirect utility functions are related. All right, so let's prove this. I mean, I'm not proving it. Let's show this with an example. So here's the example I'm going to use. Remember my ugly utility Cobb-Douglas function x 1/3, y 2/3, I guess? Yes. The price px, py, and income I, and the utility level u bar. So the last time, in the last video, I calculated the px, py, income, the indirect utility function, as this ugly... Oh no, I'm sorry. I calculated the expenditure function, not the indirect utility function. The expenditure function, px, py, u bar, was this. U bar, px power 1/3, py power 2/3, and 1/2 to the power 2/3 plus 2 to the power 1/3. By the way, this term is multiply these two, add 1. So multiply these two, it's 2 to the power 1 plus 1, 3. So it's basically u bar 3 divided by 2 to the power 2/3, px to the power 1/3, py to the power 2/3. All right, this is the expenditure function when the utility function is the Cobb-Douglas function with 1/3, 2/3 weights. Okay, so now I want to find the indirect utility function, px, py, and it's a function of income. All right, so let's find this. Here, by the way, in this notation, P is the price vector, I mean Px, Py. Okay, so how do I find the indirect utility function? Remember, the indirect utility function is a solution of the maximization problem. Maximize U, X, Y, subject to the budget constraint, Pxx plus Pyy equals income. So the Lagrangians, I'm going to be a bit speedy here. My Lagrangian is utility minus lambda times constraint. So therefore, the first order conditions are del L del X, which is equal to, remember my utility function is the Cobb-Douglas. So it's 1/3 x to the power minus 2/3 y to the power 2/3 minus lambda px equals 0. Del L del y is equal to 2 to the power x 1/3 y minus 1/3 minus lambda py equals 0. And finally, del L del lambda is equal to pxx plus pyy minus income equals 0. So if you simplify those two, you're going to have lambda px equals 1/3 x minus 2/3 y 2/3. And here I'm going to have lambda py equals 2/3 x 1/3 y minus 1/3. So divide both sides. Lambdas will cancel out. 1/3, 1/3 cancels out. This is going to be x. This is going to be y. So basically that means px over py equals y over 2x. Cross product 2x px equal y py. I'm going to use this, plug it into the budget constraint. So what I'm going to get is pxx plus, instead of y times py, I'm going to write 2x px equals income. So therefore, x is equal to 3x px. So income divided by 3px has to be the optimal. So this is the optimal Marshallian demand. Later we're going to call it. So once I find it, what is y? Well, y is 2 times this px divided by 3, and I'm going to cheat. It is 2 income divided by 3 py. All right, so these are the optimal levels. So once I plug them back to my utility function, which is u of xy equals x to the power 1/3 y to the power 2/3. So whenever you see x, put this. Whenever you see y, put this. So my indirect utility function, again, I'm going to cheat, is going to be equal to income divided by 3, 2 to the power 2/3 divided by px to the power 1/3, py to the power 2/3. So this is what my indirect utility function will look like. Okay? So now I need some space. So I'm going to show this one and then this one. All right. So first off, what is VPI? So VPI. The price regime is PXPY, income is I. All right. Well, it's given there, right? I over 3, 2 to the power 2/3 divided by 3 is there. Px to the power 1/3, py to the power 2/3. Very well. So whenever in the expenditure function, PVPI is therefore, whenever you see U bar, okay, so whenever you see U bar, just plug this, all right? So whenever you see, so this is the maximum utility I am gonna get. So therefore, whenever I see U bar in my expenditure function, I'm gonna plug this. So remember my expenditure function is this, right? Which is 3 divided by 2 to the power 2/3, px to the power 1/3, py to the power 2/3 times U bar, times U bar. So whenever I see U bar, again, plug this, which is income divided by 3, 2 to the power 2/3 divided by px to the power 1/3, py to the power 2/3. So this is U bar once again. So make the simplifications. 3's will cancel out. 2 to the power 2/3 will cancel out. Px 1/3 and py 2/3 cancel out. The only thing that remains is income. All right. So therefore, my expenditure function calculated when U bar is equal to V of Py. All right. This is exactly what it says. Expenditure function calculated when the U bar is equal to, right, Px, Py, U bar. So when U bar is equal to V of Pi, must be equal to income. Check. This is true. Now I'm going to show or verify this. What does that mean? Look at the indirect utility function. Whenever, so P is the P, so Px, Py, leave them. Whenever you see income, you have to plug the expenditure function. At the end, you must get the U bar. Let's do this. So I'm going to clean this part. So what is my, so VPXPY, E of PXPY U bar. So whenever you see income, just plug the expenditure function. So this is my V function, right? Write everything except I, the income. So it's 2 to the power 2/3 divided by 3 times 1 over Px to the power 1/3, Py to the power 2/3 times income. So now whenever you see income, just plug the expenditure function. So it's 3 U bar divided by 2 to the power 2/3 times Px 1/3, Py 2/3. Okay, 2 to the power 2/3 cancel out. 3's cancel out. Px 1/3, Py 2/3 cancel out. What I have, 1 times U bar, which is simply U bar. So the indirect utility function evaluated at your expenditure level to attain U bar must be exactly equal to U bar. Okay? So, that's very important conclusion. The indirect utility function and the expenditure functions are related. And this is how they are related. And if we need to read them, it says the minimum level of expenditure or the minimum amount of money you need to attain the maximum level of utility you can attain with income is the income itself. And the maximum utility level you can get when the minimum expenditure to attain U bar is actually U bar itself. I think it's also quite intuitive, but obviously it's possible to give a formal proof, which we are not going to do in this course. All right, I hope that was clear and hope to see you next time.